for joining. My name is Alberto Vieira. I do developer relations at Moonbeam, even though I'm part of a company called Papermoon. And this talk, by the way, is a similar talk that I gave at ETC. But yeah, I wanted to sort of share it here as well because it's a very interesting talk. It starts very generic, not really specific to Moonbeam, and then we'll slowly dive down into more cross-chain calls with Moonbeam. I think I was part of a Whaler DAO presentation probably a month ago or so, and this presentation is very complementary to that. So if you've never heard about Moonbeam, I recommend you to go and check that video out because some concepts might not be familiar to you if you've not seen that presentation before. So yeah, let's get started. So as the introduction said, the presentation is entitled Cross-Chain EVM Calls in a Multi-Chain Future. But yeah, before we sort of go into like the EVM calls in a cross-chain future, we need to understand why are they important, right? And so to understand why cross-chain EVM calls are important, we need to understand the current sort of like landscape of blockchain technology. Basically, we can confidently say that the future, it's multi-chain and it's cross-chain. And one of the main reasons for this being this way is that you have the tech stack for building blockchains has made building blockchains quite an easy process. What I mean by that, if we look at this plot in which you have time in the x-axis moving from left to right, and then you have the number of blockchains sort of represented vertically, you can see that initially there were very, very few blockchains out there. It was really hard to build a blockchain from scratch. You had Bitcoin, you had Litecoin based on Bitcoin. Then later on, you had others like Ethereum. And so it was really rare to see new blockchains coming up, But as new tech standards like the Cosmos SDK, Substrate from Polkadot, also, for example, the OP stack from Optimism, right? These development environments or SDKs provide a way to create blockchains in 10 minutes, right? You have basically building blocks that allow you to build a blockchain with all the necessary components in a matter of minutes. And so now you can focus on what you want to build your blockchain, on what topic you want to build your blockchain on, right? You can customize your blockchain to address certain niche and things like that. And so we can clearly state that, before it was not that easy to create blockchains, and now it's really, really straightforward. And so we've seen the shift, new blockchains popping up that are addressing a specific niche, specific sort of markets, right? We've seen, for example, blockchains that are specific to prediction markets, blockchains that are specific to DeFi, blockchains that are specific to multi-sig wallets and things like that. And so in a cross-chain, multi-chain environment, we've seen sort of two typical strategies in the current sort of state when you talk about multi-chain deployments, right? So let's say I'm a smart contract developer, I created my application, and I want to call myself multi-chain. And so one of them is what we like to, describe as centralized deployments, in which I have my set of smart contracts deployed to a single blockchain, let's say Ethereum or Moonbeam, and I'm asking all my users or all the users that want to interact with my deployment to bridge their liquidity, their whatever it is, to my project, right? And so basically this is what we call the centralized deployment, because in this scenario, you only have your contract deployed in one blockchain, and then you have basically, you're centralizing the experience and the security to one blockchain. The other type of deployments that we like to describe as multi-instance deployments. I think this was fairly straightforward. It's a fairly straightforward concept, and I think SushiSwap was one of the first projects that actually did this, but other projects soon followed, right? I can call my project multi-chain if let's say Alberto project multi-chain is now multi-chain, because it is just basically I grab my contracts and I deploy them everywhere. I'll deploy them to Moonbeam. I'll deploy them to Ethereum. I'll deploy them to Avalanche, right? And so now my project gets multi-chain, but that's not really true because you're fragmenting users, you're fragmenting liquidity, you're basically fragmenting features and experiences, right? So each of these deployments have their own like pros and cons. On the left-hand side, it's a lot easier to manage, but then you have the bridging security, a limited market, because people might not be willing to take the risk of moving their assets, for example, to another blockchain. And then on the right-hand side, we have basically, okay, to solve the problems of a centralized deployment, we'll just basically throw our contracts everywhere. But now it's a lot more complex to maintain the project. You're fragmenting users because you don't have a single community. And then just overall, it's really hard to sort of deal with all these like deployments from a user perspective and from a developer perspective. This is a slide that I was mentioning about the tech standardization and number of blockchains. So you can see here that as these tech standards were created, there are more blockchains out there. And this is the other slide that I was referring to, right? On the left-hand side, you have centralized deployments, in which you have multiple blockchains, and when you're asking users to move to a centralized, basically, set of smart contracts. And on the right-hand side, you have a multi-instance deployment in which your contracts are everywhere, right? Cool. So let's continue. So the way to solve this problem that we're actually referring to now is through something that in Moonbeam we describe as connected contracts, in which basically you can reach any asset, any user, or any service through this strategy, right? And so ideally, even though that this looks very similar to the multi-instance deployment that we're actually mentioning before, this is quite different because in this case, you have a set of smart contracts deployed to Moonbeam, for example, and another set of smart contracts deployed to other blockchains like Ethereum, Avalanche, Polygon, etc., right? And the main difference here is now that you have smart contracts that act only as like gateway, basically, right? So this means that you have things like, for example, a smart contract in Avalanche that can communicate to your core smart contract on Moonbeam that an action happened, okay? So this means that you can, for example, say, okay, let's say that you have an NFT marketplace that is multi-chain, but I'm talking about truly multi-chain, right? Where, for example, all the logic lives on Moonbeam, but then users, for example, from Avalanche can actually buy an NFT, then it's the buy order is processed on Moonbeam, and then there's cross-chain messages communicating both blockchains, stating the action from the origin user into the core smart contracts on Moonbeam. So the main benefit of this is that you don't have the risks of centralized deployments, where you're asking users to basically bring their assets or experiences to one single blockchain, but you don't have just a bunch of similar smart contracts deployed everywhere. You basically have the pros, each of these different type of deployments. And by the way, all that I've mentioned up to now, I've actually mentioned it before in the Moonbeam presentation that I did roughly a month ago. So this is where we start like discussing new topics, right? So the key innovation that allows connected contracts to actually exist, it's called general message passing. With general message passing, basically blockchains can be aware of other ecosystems. In the current technology, with the current technology, each blockchain is completely isolated from the other one, right? So basically, blockchain one with its consensus and everything has no clue that blockchain two exists. This means that a smart contract on blockchain one cannot really know or cannot really interact with a smart contract on blockchain two. But if you add something called general message passing, you can actually do cross-chain calls, meaning that, a smart contract on blockchain one, it's aware that, blockchain two exists. And it's also aware that a smart contract on blockchain two now exists, right? So you can have, like I said before, a smart contract on blockchain one can now interact with the blockchain two and then create multi-chain experiences that just provide better UX for the user. And the cool thing now is that this opens up just a bunch of possibilities if you think about it, right? You can have basically endless combinations of things, but the idea is always to try to keep the user experience as seamless as possible, even though the infrastructure component of it, it's quite complex, right? And now blockchain two benefits as well because, it could also sort of interact with other blockchains as blockchain one was doing it now. So to understand how this works at a very, very high level, we need to understand a little bit of consensus and cross-chain, right? Because, originally it's quite easy to understand because you have blockchain one, which is with its own consensus mechanism, and then blockchain two, which is other consensus mechanism, right? You can think about these like Moonbeam with the Polkadot consensus, and then you have also Ethereum with this proof of stake consensus, right? And once again, think about that, these two consensus mechanisms or blockchains don't really know each other. And so at a very high level, this is very generalized. This is not completely true. But how general message passing works is that you can actually connect these isolated consensus systems. And so now basically, if blockchain 1 wants to send a cross-chain message, there will be an intermediate consensus or a general message passing protocol that will be able to plug that cross-chain message and listen to it from blockchain 1. And it's also able to plug to basically the blockchain 2 and then execute that cross-chain message on blockchain 2. All right. And so now this is really interesting because you have consensus 1 that has no clue that consensus 2 exists, but the consensus of the general message passing protocol is aware of both consensus, right? So it's able to communicate an action on blockchain 1 to something happening on blockchain 2. And so sending now the image from before, right, where you have basically 3 consensus working together, let's understand a little bit of how can blockchain 2 trust blockchain 1, basically, right? How different cross-chain calls are verified. And the one of the probably most complex ones that it's not really that used, it's called the native verification, which is light clients and Merkle proofs, okay? So basically, once again, you have 2 consensus mechanisms that are completely independent, sovereign, and have no clue that the other one exists. But then you have basically a set of relayers that are just moving messages from one chain to the other chain, and they're executing the messages and so on. But one important thing is that these messages are not being verified because the relayers don't really have like a consensus mechanism, right? And so one way to add a consensus on top of this is through something called light clients. And light clients, the easiest way to understand them is that basically, if you're running a light client in blockchain 2, that it's running blockchain 1, typically the light client, instead of having like the entire copy of the blockchain 1 to verify the message that was sent from it, it will only have the minimal, most critical components to verify that what's happening in blockchain 1 is valid, okay? So it is running like a very minimized consensus. Basically, if it happens on blockchain 1, blockchain 2 will be actually aware that a message in blockchain 1 happened. And it's going to be able to verify in a very, simple way that the message on blockchain 1 actually happened, it was executed. And then basically when the message execution happens on blockchain 2, it allows it to happen basically because what happened on the blockchain 1 it's valid. There are, I would say, one of the most prominent protocols that is using this native verification mechanism is Cosmos with IBC, right? So once again, this is very general. Cosmos IBC has a very sort of particular way of handling this native verification. So this diagram might not be valid for Cosmos, but as a general idea, this is how like Cosmos IBC works basically. Each blockchain is running a light client and a sort of like a minimized consensus of other blockchains. And you're not actually trusting in an intermediate consensus mechanism like what I showed before. And so that the most common applications of native verification is light client, which is the one that I just showed you here, or some type of Merkle proofs, which is similar to light clients. They're just different ways to sort of state the same thing, right? The other type of cross-chain verification mechanism, it's what it's called external verification, right? And this is the same diagram that I showed before, in which you have some sort of relay mechanism that it has its own consensus, and then optimistic bridging as well. It's very popular right now on L2s on Ethereum, because basically, whenever you pass a message from blockchain 1 to blockchain 2, you have an external party that is in charge to ensuring that the message actually happened and that the message gets executed, okay? Especially that the message happened on blockchain 1. So think about that you have 2 ways basically to verify messages, cross-chain messages. One is a native verification and the other one is the external verification. There are multiple subsets of each. You can have CK proofs on top of it and so on, but as a very general idea, this is how they work, okay? So now we talked about different cross-chain messages verification mechanisms, let's go through some examples of different cross-chain protocols. The first one that we can talk about is Axolot, which is using it's an external verification They use an external verification mechanism on top of their proof of stake consensus, basically. All right, so let's say an app or a user on, let's say, for example, Moonbeam wants to interact with another blockchain through Axolot. Basically, they will interact with what they're called gateway contracts. And the gateway contract will communicate more or less with the proof of stake consensus mechanism through like relayers and things like that. And basically, the proof of stake consensus mechanism that Axolot is running as a Cosmos SDK based chain, it's able to verify that, through basically a proof of stake method consensus, that I think it has slashing and everything. And basically it's able to say, okay, we can all agree through our proof of stake consensus that message is valid. So we can actually execute it on the destination chain that the message was intended to be executed. And then you have some sort of relayers that are basically going to grab that message and are going to execute it in whatever network it was destined to. Let's say, for example, Ethereum. And this Axolot has its own sort of benefits. It's using chain agnostic packet translation and delivery. It has a really sort of unique way of dealing, for example, with token transfers, in which you actually send the tokens to an address on a contract, and then everything is taken care of for you. They have very flexible way of handling fees, and they actually are connected to Cosmos via IBC, right? So it's really sort of you can actually connect to any Cosmos chains if your blockchain is integrated with Axolot. Back in the day, you had to run your own relayers, which actually, I'm not sure if back in the day, but you have the possibility to run your own relayers if you don't want to sort of rely on external relayers. Note that relayers in this case, they can only censor the message from being passed. They're not used to actually verify the message. But Axolot has its own relayer network as well, so you can just trust their own relayer network. Layer 0, it's a little bit of a mix between external verification and like native verification, right? Because it uses something that they refer to like ultralight nodes, which is like a little bit of like light clients that are actually on chain, but they actually rely on external verification because you have external parties that you need them not to collude to ensure that the message is passed correctly, okay? So the way that layer 0 works at a very high level is that you have apps and users that are interacting with the layer 0 endpoint, and basically the layer 0 endpoint will basically emit the message to the ultralight nodes. I think these are contracts. And then you have two separate components. You have a relayer that will submit the transaction proof, so that the proof that the transaction happened on the origin network will actually submit it to the destination ultralight node contracts. And then you have the oracles, which are just submitting block headers, right? And so with these two components, the ultralight node component on the destination chain can verify that message it's actually valid, and it will execute it on the destination chain. So as long as the oracle and relayer don't collude, so they don't know each other, they don't trust each other, and they just work independently, this mechanism is okay, because the oracle doesn't get anything from submitting faulty block headers separately, because the transaction proof will not match. Or the other way around, right? If the relayer is malicious and submits a fake transaction proof, then when the oracle submits a block header, the transaction proof will not match with the block header, right? And so basically, there's a way to basically verify if each of these parties is actually malicious separately. And as long as you have one non-malicious oracle or relayer, the implementation works. So basically, the way that layer 0 puts this is that as long as you have one honest component, it will not, it will work. And so this is really interesting because you don't really have like an external colluding basically against your cross-chain message. So I think this is another really interesting sort of approach. I think they're using, for example, really reputable oracle providers like Chainlink. And so as long as you trust Chainlink's oracles, which they have proved to be quite cross-chain verification mechanism, it's bulletproof, right? Yeah, and last but not least, we have a Wormhole, which is once again very similar in terms of diagrams. You have basically apps and users interacting with Wormhole contracts, and the Wormhole contracts will emit events that are picked up by a proof of authority consensus. The proof of authority consensus works basically by just having really well-known operators of the consensus, right? So you have entities that have a reputation to lose. And they are basically verifying the messages, right? If the entities basically collude and they become malicious, they will lose a reputation, let's say in the business, and so on. And so they don't really have, it's not in their best interest to actually collude when verifying the message. They have very high number of validators, meaning that I think it's like around more than 25, I think it's 27 or 29. And they have also a really high multi-sig threshold, meaning that, very high number of entities need to approve for a message to go through, right? So even if 1 or 2 or 3 or 4 entities are turned malicious, it doesn't really matter because you have a very high multi-sig threshold. And I think they launched like a couple of weeks ago the relayer network, right? So before, like with Axolot, you can run your own relayer so that you can trust your own system and you don't rely on external providers. But they provide a relayer network as well. And I think they're also moving toward their own consensus mechanism on top of their own blockchain. But yeah, I mean, right now they're based on a proof of authority consensus. In the future, they might not be. So, I mean, this slide might be wrong in a couple of months. So yeah, I mean, I just wanted to give to you those 3 sort of bridging examples so that you understand the report. It is super helpful. It has a lot of like very detailed information about different bridges. This is Unisop's opinion on CrossChain protocols, right? This is just their opinion. But yeah, I mean, it has a lot of great information. Cool. So now let's go into Moonbeam, right? I mean, this was a Moonbeam related talk. Everything that I said before was very generic, but the idea is that you understand a little bit of how Moonbeam does CrossChain calls inside Polkadot compared to, for example, all the things that we just discussed before, right? So the first thing that you got to understand is that the CrossChain language that it's Polkadot uses is known as XCM, right? And so basically when a parachain or Moonbeam, let's say, wants to communicate to another parachain, let's say like Hydra DX or Interlay or A-Star or whatever, it uses, basically it sends what it's known as an XCM message, okay? And so, but both parachains are connected to the same relay chain or Polkadot. And actually Polkadot is what provides security or consensus to these parachains, okay? And so basically Moonbeam, it's already relying Polkadot to verify the new blocks or the state transitions that happen on Moonbeam. And then the other parachain is also relying on the same consensus mechanism for it to check this cross-chain its own blocks and so on. And so now when Moonbeam wants to send an XCM message to, let's say, parachain B, you can clearly see how this picture or this diagram actually differs from the one that I was showing before. Because before you had to trust, for example, one consensus had to trust the other consensus, or for example, both consensus had to trust an intermediate consensus, right? In this case, parachain A and parachain B are already trusting Polkadot the same consensus for security. So basically when they send a cross-chain message from parachain A to parachain B, it's already trusting Polkadot for its own security. So it should trust Polkadot for, parachain A security as well. And so this becomes a less of a, it's a bit more decentralized how this cross-chain architecture works when, parachains are interacting with each other. And so, XCM execution results in state changes. State means, if Alberto had, 10 tokens on block X, and then it transferred, 1 token to parachain B, it should have 9 tokens in the next block, right? And so basically, the state changes happen in both parachains are verified by the same consensus, which is the whole concept of Polkadot when they actually say shared security, right? You have Polkadot security being shared among different participants of the ecosystem. And so now that we understand sort of like why Polkadot architecture is so beneficial for cross-chain, let's now get into the fact of what XCM is at a very, very high level, okay? So XCM, from a very practical and simplified perspective, it's a cross-chain message, okay? So it's a message that goes from parachain A to parachain B with a set of instructions, okay? The instructions can be, hey, parachain A, can you take tokens from Alberto's account and put them in this special location. And please send a message to parachain B saying XYZ, right? And so basically, parachain B will receive this message, we'll open it up, and we'll see the instructions that are specific to parachain B, like, okay, Alberto actually locked these tokens on parachain A. Now actually let's, execute this call on his behalf, right? So what's important for you to understand is that XCM is basically a message with instructions that gets passed from one parachain or blockchain to another parachain or blockchain, and these instructions are partly executed on parachain A, partly executed on parachain B, but the combination of instructions is what results in concrete actions. Okay, so if you need me to, for example, turn on the light in the office that I'm at right now, you cannot just simply tell me turn on the lights, right? You need to tell me, hey, Alberto, stand up, walk to the right 10 steps, flick the switch, and then the light will turn on, right? And so a combination of instructions result in something actually concrete. So for example, if you want to transfer assets between Polkadot blockchains, you need to send this following instructions, right? For example, on parachain B, on parachain A, you need to send this instruction that is called transfer reserve asset, and this is going to do certain actions on parachain A. And then on parachain B, you need to send the following instructions that by themselves don't really mean a lot, but the combination of instructions is actually what results in, for example, a user on parachain A sending tokens to a user in parachain B. Or for example, if you want to do remote execution, which is what's really cool here, you actually just, let's say, for example, in parachain A, you might not need any instructions. And in parachain B, you need to include these 4 instructions, which are like the core instructions, so that you can actually, in the transact instruction, you actually tell blockchain B, hey, go to this smart contract, for example, and execute this function call. So these 3 instructions before the transact are just like, the introduction that it's needed so that you can actually remotely execute something on another parachain, right? And this is really interesting because, on Polkadot right now, you can actually do remote EVM calls via XCM. So let's say that you are a blockchain on Polkadot that you don't have an EVM, but you want to execute something in some smart contracts, right? So you can actually just, via XCM call Moonbeam's EVM. And, one concept that you need to understand for, cross-chain EVM calls on Polkadot and Moonbeam, it's basically the concept of sovereign accounts. The sovereign account is basically, it means that parachains have accounts on other parachains, basically. Okay, Moonbeam has an account in Interlay, Hydra DX, A-Star, Akala, Parallel, whatever other blockchains, right? So Moonbeam has an account in all of these other parachains that it's a keyless account, so nobody knows a private key, but basically it's controlled by the entire blockchain through, for example, governance, right? So if Moonbeam wants to use its sovereign account on Hydra DX, it will actually need to do a governance proposal on Moonbeam and say, hey, let's grab our sovereign account on Hydra DX and execute this action there, okay? And so basically when an XCM message is sent from, let's say, Moonbeam to Hydra DX, the XCM message is executed. So the message sender of the execution of the XCM is that account that it's known as a sovereign account, okay? And that it's great, but sometimes it's not safe, right? Because remember, imagine that you want, a user on Moonbeam to interact with Hydra DX. You don't want it to interact with Hydra DX through the Moonbeam sovereign account, because that could be dangerous, right? Because it's basically representing the entire Moonbeam blockchain. So you might need to sort of mutate or change that origin or that message sender to be something else. And that's what we're going to discuss next, basically. So yeah, remember, the sovereign account is an account that each parachain has in the other participants of the ecosystem. And when an XCM message is being executed, on a certain parachain, the message sender is that, origin parachain sovereign account. So in order to sort of enable the possibility of Alberto on Moonbeam being able to interact with, let's say, Hydra DX without using Moonbeam's sovereign account, XCM introduced a concept of remote dispatchers. It has many names: computed origins. We used to call it multi-location derivative accounts. to be honest, I think remote dispatchers is also fine. So it's just many names for the same solution, which is basically when a user on Moonbeam sends a cross-chain message to other blockchains in the Polkadot ecosystem, a special instruction, a special XCM instruction, it's included. So, I mean, if you don't include this XCM instruction, Moonbeam will not allow you to send an XCM message. And this XCM instruction on when this XCM message gets executed on the destination blockchain, this XCM instruction will change the message sender, okay? And so what this means is that Alberto on Moonbeam can now control deterministic accounts that are generated basically for him with this XCM structure, right? So if Alberto wants to interact with Hydra DX, he will send an XCM message that will include the send origin instruction. And then when Hydra DX executes this XCM message, it will understand, oh, okay, so I need to actually change Moonbeam's sovereign account as the message sender. And so I will change it to whatever it's included in the send origin. In this case, it's basically a pointer to Alberto's account on Moonbeam. And so that way, Alberto will have now, every time that it sends an XCM message to Hydra DX, it will have a remote dispatcher on Hydra DX that can only be controlled by XCM from Moonbeam, okay? And so this is really cool because from Moonbeam, you can actually do actions everywhere, right? You can do actions on Hydra DX without actually having to switch your wallet, go to Hydra DX and do the action there directly. And yeah, this opens up the possibility of doing, you know, many things, right? For example, an account, a person with an account on Polkadot could control an account on Moonbeam to interact with the EVM, to send funds via a bridge, to go into DeFi on Moonbeam, to do a staking on Moonbeam without actually having to have a Moonbeam wallet, right? So using the Polkadot wallet that he prefers, if someone builds a dApp that, you know, enables you to stake Glimmer, the Moonbeam token, from Polkadot, you know, you will be able to do it via XCM, which is pretty exciting, right? Because I feel that one of the core ideas of connected contracts is the idea of hiding infrastructure complexities for cross-chain interactions, right? And so basically, if a user on Polkadot would like to stake Glimmer on Moonbeam without this idea, you actually would have to, you know, move your tokens from Polkadot to Moonbeam, swap, for example, DOT to Glimmer, and then switch your wallet to that account and then do the staking. But if you create a dApp that actually uses this XCM mechanism, you can actually use this you can actually do this from Polkadot. Other applications could be, for example, accessing the centralized Bitcoin through Interlay, or accessing the Hydra DX Omnipool via XCM and things like that. And actually, one really cool scenario that the Hydra DX team is doing now, it's sort of like allowing parachains to deposit assets from their treasury to the Omnipool to earn a little bit of yield, right? And this is using basically XCM and this remote dispatchers, basically, right? So basically, Moonbeam, it's controlling via governance its sovereign account on Hydra DX to create a position in the Omnipool and deposit liquidity there, all trustless via XCM, which is fairly cool. So now we get to the last point of the presentation, which is CrossChain EVM calls via XCM. I know that I'm a little bit behind schedule, but we'll just move quickly through this. So to understand how CrossChain EVM calls work via XCM, we need to understand a little bit the process of how regular EVM calls work on Moonbeam, right? So when you are connected with MetaMask to Moonbeam, and you're interacting with it from MetaMask, what's happening is that this is actually connecting to Moonbeam's Frontier RPC extension. So let's say you want to send a transaction, some tokens to someone on Moonbeam. And basically, this Frontier RPC extension, which is part of Moonbeam, will actually interact with something called the Ethereum module. This will actually validate a transaction and send the validated transaction to the Rust EVM through something called the EVM module, okay? And so basically the EVM module is what allows the Ethereum module to access the EVM, which is this state transition machine that we know from Ethereum. Once the transaction gets executed by the EVM, there will be just some EVM execution results and some Ethereum logs. Like, for example, hey, your transaction hash is this one because you've successfully transferred, one token from Alberto to Alice, right? This is fairly straightforward because everything happens in one single blockchain, right? But what happens when you actually, from let's say Hydra DX, you want to use Moonbeam's EVM via XCM. And so now the flow changes a little bit, right? So now the user or the dApp is actually on a separate chain that it's using its own consensus, its own signature. So let's say there you're signing with apples and you're not signing with like the Ethereum or the Moonbeam way, right? And so, what happens now is that Moon cannot really sort of trust the signature of the origin chain person, right? Because there's no signature information. It's passed with the XCM. But basically what we do is that we use this remote, if you remember the descent origin instruction, we calculate a new dispatcher, so a new message sender from the XCM message, basically. And then this XCM message gets checked by a new module called the Ethereum XCM module instead of just the Ethereum module, right? So this Ethereum XCM module will do the transaction checks before going to the EVM. And then this Ethereum XCM module will call the Ethereum module to send the valid transaction, okay? And now the flow, it's fairly similar, basically. Now the EVM will actually process this, and then the Ethereum logs will pop up here. And so the only true difference here is that because the XCM, the EVM action is executed through XCM, there's no signature component on the transaction on the EVM side. So the signature is first basically invalid. It's like 0x1s, and the gas price is 0 because you're paying the transaction fee in XCM execution and not at an EVM level. Okay, that is important to understand because if you check, for example, the Ethereum log, the gas price will be 0, and you will be like, oh wait, did I just did this for free? No, because you're actually paying it some other place, right? And that you cannot do, for example, easy recover to get the signer because the signer actually was in a completely separate chain. And so that is basically at a high level how CrossChain EVM calls through XCM work. This is actually live in our testnet right now, and you can actually use this scenario that I can present here as the last sort of like slide, in which you can use Moonbeam as a gateway in and out of the Polkadot ecosystem. Moonbeam is launching something called the Moonbeam routed liquidity that is going to launch with Wormhole first, in which, for example, parachain teams like Hydra DX, Manta, Interlay, and others are going to get liquidity through Moonbeam in a one-click experience. Basically, a user on Ethereum will be able to send liquidity to Hydra DX by just signing a transaction on Ethereum. And then on the way back, if the user wants to remove its liquidity, it's going to using remote EVM calls through XCM, it's going to be able to remove that liquidity from Hydra DX and then indirectly call the Wormhole bridge contracts, through Moonbeam to get it out. And so, Moonbeam it's uniquely positioned to be the sort of gateway in and out of the Polkadot ecosystem through the major GMP protocols like Wormhole, Layer 0, Axolot, Hyperlane, and others that are coming as well. So yeah, I think that was the last slide. You have the actual URL to the slides here. So sorry about the hiccup at the beginning of the presentation. If you want to learn more about Moonbeam, you can follow us on Twitter, Moonbeam Network. The Telegram channel is Moonbeam_official. Also the Discord, and visit the website. You can contact me in Telegram at AlbertoV19 or via Discord at TheAlbertoV19. So yeah, I hope you liked the presentation.